Okay, so we finished talking about Frank Kamenetsky theory, and now we're going to start discussing detonations and the Rankine-Hugoniot relations. First, we discussed the Rankine-Hugoniot relations. For those of you who've taken gas dynamics or compressible flow, these are actually the exact same thing, only we're going to extend the Rankine-Hugoniot relations that you may have learned in compressible flow and extend them to a reactive fluid, or really a reactive material rather than, I need to be specific here, because we are discussing combustion of solids and liquids in this class. So, so here we are going to consider, for the Rankine-Hugoniot, we're going to consider a pre-mixed combustion wave in an insulated constant area duct. So you could imagine that we have a tube filled with a mixture of something that'll burn by itself. It could be RDX, it could be an explosive of some sort, or it could be a pre-mixed mixture of fuel and oxidizer. So say you could have a mixture of hydrogen and oxygen here, and then you could imagine basically lighting a match at the end of the tube, and then basically watching how the combustion wave travels down the tube. Okay, and so you can imagine here that there'll be an unburned state and a burned state, and there's a whole bunch of stuff that happens between the burned state and the unburned state. But for Rankine-Hugoniot, all we are concerned about is characterizing the burned state and how fast the wave moves relative based on the unburned state and your chosen equation of state. Okay, so for the unburned state, I'm going to call that state 1, and that will have some initial temperature, some initial species composition, some initial pressure, and some initial density, and also some initial specific volume. You'll find when you work with the Rankine-Hugoniot relations, the equations are more natural in terms of specific volume rather than the density, which is something that as mechanical engineers we're not quite used to. But the Rankine-Hugoniot relations themselves are more natural to work with in specific volume. And so state 2 is the burn state. So here we have some some products that are being produced by the motion of this combustion wave. And when I say combustion wave, I mean in general both detonations and flames, which is, or if I want to be technically correct, deflagrations, which we're going to talk about later on, are both combustion phenomena. And so sometimes you hear people saying that detonations are not combustion, which is kind of bizarre to me. So, but they're both combustion. So this combustion wave is going to basically propagate through the unburned state, and as a result of the chemical reaction, it's going to be converting the unburned state to a burned state. And this burned state will normally be at a vastly different temperature, a different pressure sometimes if it's a detonation, and a different density, and also a different chemical composition. If the chemical composition is unchanged, then it was not a combustion wave. Okay, and so really what we are after here is what is state 2 given a state 1. That is, if we're given a mixture of stoichiometric hydrogen oxygen at 300 Kelvin in 1 atmosphere, and we burn it, what types of combustion waves can we expect to see, or can we see, and then how fast do they travel? And so we were interested in finding those. And so this here, I was sort of considering that the motion of the unburned state was stationary, and we have some wave propagating through it. But just like in gas dynamics, you work in what's called the wave fixed frame, where basically instead of the wave basically moving, and instead of chasing this wave around, you are going to look at we're going to do this analysis from the point of view of a stationary wave. And so you could imagine that we have some product flow basically going to the right, or in general going to the right, but not always. And so what we're going to do here is we're going to look at it such that we have the reactant state flowing into the wave, and the wave is stationary, and so basically it's just not moving. And the products are then the products just exit the other side of the wave. Okay, and so I kind of flipped it, but now instead of the wave traveling, we have the product, or we have the reactants flowing into the wave. Okay, and so we are essentially choosing our velocity at V1, or the velocity of the reactants to be identical to the velocity of the wave if the reactants were basically stationary. And so basically what the wave is trying to do is the wave is trying to propagate is trying to propagate to the left into the reactants, but we are choosing the velocity of the reactants to be exactly equal to the velocity that that the wave is trying to propagate. And so basically the absolute velocity of the wave is just given by basically this expression here, and by our choice of u1, this is equal to 0, and so the wave basically stays put. And you can relax this so that the wave can move at any arbitrary velocity relative to the flow. And you probably did something like that in compressible flow, where you dealt with moving shock waves. But in the end, most of the analysis was done with a stationary wave. And so this here is the exact same concept. But when we discuss explosions towards the end of this class, we will be dealing with moving combustion waves because explosions have a definite fluid motion behind them, and you need to consider that in their analysis. Okay, and so what we are interested here is really just analyzing the bulk features of the combustion wave. We don't care about all the goings on inside of the combustion wave at this point. There's a whole lot of things. There's a whole lot of structure, all the chemical kinetics, the molecular transport, shock physics, etc., etc., etc. All occurring inside of this wave. And basically we're going to do a control volume analysis, and we're going to choose our control volume such that all of that garbage that we don't know about is inside of it, and we don't need to worry about it. Okay, and so essentially what we're going to do is we're going to choose a very large control volume, something like this. And so why large? Because normally when you think of a shock, you're choosing a very small control volume, but here we're sort of choosing a large control volume. Okay, and the reason I say that it's large is that it needs to be large enough to contain the entire combustion wave. Okay, and so if our control volume is inside of the thickness of the combustion wave, then we've done no good. Okay, and so just sort of heuristically, we are choosing it to be very large, between x is plus or between x is from minus infinity to plus infinity, and then we'll do a CV analysis, or there's another way to derive these, and that's to actually work with the governing equations in one dimension and then basically integrate them. And so, and then also, why do we choose this? So why do we choose our control volume being large? Two, if there is a theoretical infinite distance for the chemical reactions to occur, we can assume that the products are at their full chemical equilibrium state. That is, since the reactions have had an infinite amount of time and distance to complete, the products are at full chemical equilibrium, and they're not in some in-between state between the reactants and the fully equilibrium state. They're at full equilibrium. Also, if we choose our control volume to be huge, we can also guarantee that there are zero gradients to the flow on the edges of the control volume. And so basically dt dx, du dx, etc. are zero on the edges of our control volume. And that will, and that means that on the edge of the control volume, we don't need to worry about heat conduction on the edges here. We don't need to worry about viscous stress on the edges here. And we also don't need to worry about species diffusion on the edges here. And so that's another reason that we choose a large rather than say a small control volume. But in our control volume, we only have this one wave. And so even though mathematically we're taking it to plus and minus infinity, in reality, it may be very thin. Okay, and we're also going to assume steady state, and that's an important assumption. And so we are assuming that that there's steady state conditions inside of our control volume. Okay, and so when we do the control volume, we have the wave here, and v wave in the wave fixed frame, the velocity of the wave is 0. So we have some flow of reactants going inside of the control volume, and some flow of products coming out, and also inside some chemical reactions. Okay, and just by the way, I've written this here. I am including the enthalpy of formation inside of the enthalpy here. Okay, and so if you were to not include the enthalpy of formation in the enthalpies going in and out of your control volume, you would also have to include a Q dot term to account for the chemical energy. Okay, so are there any questions with this? Okay, so again, for those of you who've been through comp flow, this is the identical procedure, basically that you did. For that, when you derived Rankine Hugoniot, and it's no different here. So here we're going to do a control volume analysis, and I'm going to show probably at least 2 different ways of deriving these. And like one is based on the formal PDEs, which is the way a physicist or a mathematician would derive Rankine Hugoniot. And I'm going to use a control volume for some of the other equations, or the other conservation laws, I should say, because that's the way that as an engineer that we're sort of trying to think about it. But if you work with detonation physics, you will be interacting with physicists and mathmaticians quite often. So it's sort of useful to see the other way to derive these. Okay, and so we're going to do conservation of mass, and that one's super straightforward. And I'm going to use the control volume approach for that. So we have some ρ1 u1 going in, and we have some ρ2 u2 going out. We're assuming steady state, and so basically we just basically note that if it's steady state, you can apply what you did in thermo, that basically m dot in equals m dot out, and that implies the expression up here where we have basically ρ1 u1 equals ρ2 u2, and in the detonation literature, the quantity, this is really a mass flux, and that's given the symbol capital M. And so I'm going to adopt that. Oops, I'm going to adopt that notation here. Okay, so are there any questions with this? Okay, and then also note we are defining x equals 0 to be at the location of our combustion wave. Okay, and so this was the control volume approach. You've seen it 17,000 times, so I'm not gonna belabor that point. Now we did conservation of mass. Now we're gonna do species mass, and I'm gonna use the PDE approach here. You can get the same result using a control volume analysis. Okay, and so for the PDE approach, what we do is we take the governing equations where we had partial rho yi partial t plus del dot equals omega dot I, and you basically expand this divergence operator for basically 1D Cartesian. Okay, and so if we expand that in basic, if we assume steady flow, this time derivative term goes bye-bye. And then we are left with basically this expression here, where basically in 1D Cartesian coordinates, the divergence operator is just nothing more than the gradient in the x direction. And because our solution is no longer a function of space or a function of time, it is only a function of space, and the space only has one is just a function of x and nothing else. We can change the partial derivatives to a normal derivative. Okay, and then we want to find a relationship. So we integrate this equation here. This is really an ordinary differential equation. And we are going to integrate this ordinary differential equation from minus infinity to plus infinity. And just recall that state 1 is at x equals minus infinity, and state 2 is at x equals plus infinity. That looks like an alpha, not an x. Okay, so I'm going to do this integral here, and this is a extremely straightforward integral because it's a perfect derivative, and so that integral here just turns into this, and then the right hand side we cannot do much with the integral of the chemical reaction rate. Okay, and so we expand this out, and we have just the species mass flux exiting the control volume, which is really what we have. 2, 1, and so this here is just the species mass flux that is leaving the control volume. This here is the species mass flux of the reactants coming into the control volume. This is the diffusion mass flux of the products leaving the control volume. And this here is the diffusion mass flux of the reactants entering the control volume. But we assumed that the edges of our control volume and at x equals plus or minus infinity that we're so far away that there are no gradients. And recall that usually the diffusion velocity of I is proportional to either the gradient of the mole fraction or the gradient of the mass fraction. Or if you're working with a real gas, the gradient of the chemical potential. But again, whatever it's a function of the gradient of, we are so far away from the wave that all gradients are 0. And if all gradients are 0, the diffusion velocities are 0 on both the upstream side and the downstream side of our combustion wave. Okay, and so these two terms go away, and I'm left with this expression here, just the basically mass flux of the products leaving minus the mass flux of, or the species mass flux of the reactants entering is equal to the integral of the chemical reaction rate. And then I can factor out basically rho u, and basically rho 2 u2 is equal to rho 1 u1, and that's just rho u, which is just capital M. And so I can say that our total mass flux times the difference in the chemical composition of the species mass fraction between the products and the reactants is equal to the integral of the chemical reaction between plus and minus infinity. And you may be worried that this is not integrable, but it is in fact integrable because essentially the chemical reaction rate has very nice properties. that essentially it will be, due to the Arrhenius term, it will be essentially almost exactly zero at x equals minus infinity. Then it'll be, then there will be some process that basically heats up the flow, and it starts to react very, 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 very rapidly, and it peaks somewhere. But then after some time, all the reactants are going to be depleted, and the chemical reaction is basically going to be killed. And so basically, you can assume that the chemical reaction is zero at both plus and minus infinity. And because of this sort of almost kernel-like feature of it, it is integrable. Okay, and mainly because the total mass rate of production of species I is zero if you are at equilibrium, and it is nearly zero if you are in the reactant state. Okay, so and so I'm just going to work with this a bit more. I'm going to divide both sides by the overall mass flux, which is the basically traditional way of writing this. And so we have our condition here that basically the mass fraction of the products minus the mass fraction of the reactants is equal to the integral of the chemical reaction rate, or the mass rate of production, divided by the mass flux. And you don't need to worry about the mass flux being zero, because this whole analysis is physically nonsense if the mass flux is zero. So you don't need to worry about that case. And also, the mass flux is just a constant no matter where we are. Even if the temperature is 300 Kelvin or 3 million Kelvin, the mass flux is still constant, because again, we are assuming a constant area duct. Okay, are there any questions so far? Okay, so we have two cases of interest. When we are concerned about Rankine Hugoniot, we don't care about doing this. When we don't care, we do not care about doing this integral. When we basically later on, when we are concerned about finding the structure of the wave, then we need to do this integral, or not really do this integral, but solve this differential equation. Okay, and so for Rankine Hugoniot, there are really two cases of interest that we have. One, we have a reactive case, and we know that because the distance between the combustion wave and the final products is assumed to be a very large distance, or we've chosen our integration point to be so far away from the combustion wave that we can assume that the final state is at full chemical equilibrium. Okay, and so basically we can conclude, because we have so much distance to do this integral here, that we have integrated the entirety of this reaction profile here, and that means that the product state is at chemical equilibrium. Okay, and basically this chemical reaction integral is just basically what makes that change of species composition possible. So are there any questions with that? So with this analysis, we are assuming that if if state one is reactive, that no matter how slowly the chemical reactions occur, state two is always at chemical equilibrium. Okay, and there is another case that we are interested in, and that is the inert case, and that means omega dot I is equal to 0, and if there's no chemical reaction, that implies that there's no change in the chemical composition between the products and reactants. And so that leads to this almost trivial solution here. And this case is not important for combustion per se, but it is important for shocks, because shocks themselves do not change chemical composition. Shocks are part of detonation waves, and so we do need to consider this case too when we are analyzing detonation waves. Okay, so are there any questions with this? Okay, then you can do the same thing with conservation of momentum. I'm gonna sort of just skip this because this is just another control volume analysis that is in the vein of what you did for fluid mechanics again and again and again. And again, we are choosing the ends of this control volume to be far enough away from the wave such that all gradients are zero, which means that which basically means that the deviatoric fluid mechanical stress or solid stress for that matter is equal to zero because there are no gradients of anything after this point. Okay, and so basically we have the flux of momentum going in, the flux of momentum going out, and then the pressure pushing on the edges of the control volume. And I'm going to skip the detail. Here I did a more formalized a control volume analysis, something along the lines of how I teach undergrad fluid mechanics is to work with this very fundamental form here. So I'm going to skip the details. You've all seen this before. And anyways, you go through the analysis, and surprise, surprise, you wind up with the exact same conditions for that you did for a shock wave. And so the chemical reaction process did not influence conservation of momentum at all. So it's still basically rho 1 u1 squared plus p1 is equal to rho 2 u2 squared plus p2. And I'm going to call this cat p. This follows D. Scott Stewart notes.
Professor, can I ask a question? Quick question.
Yeah.
When we say we're going to plus or minus infinity, so there's no gradients, does that purely mean that there's no gradients in the flow direction? Because if we were doing a multi-dimensional analysis, I mean, couldn't you still have gradients with respect to y in this? Like if you were looking at shear flow on a wall, it doesn't matter how far you go, you always have gradients in a direction.
Yeah, but this whole analysis does not work in multiple dimensions.
Right. That's why I was curious. We said that the stress was equal to zero. Is that because it's a one-dimensional flow? Or?
Yes.
Okay.
Yeah, and so you could think of, even if you had a crazy one-dimensional or a crazy multi-D flame that basically looked like this, if the flame is in equilibrium, or a small section of it, you could do this Rankine Hugoniot analysis on a very small piece. Okay, and then you assume, again, we're assuming mathematically that our control volume is very wide, but in reality, it's very thin. And so often you can assume that basically the processes locally of our combustion wave are sort of is not totally unvalid. But no, this analysis works for 1D only. In multiple dimensions, and it's 1D steady. Multi-D and unsteadiness also changes things. And unsteady effects do really interesting things to combustion waves. For shocks, you don't need to worry about that because your control volume is so physically thin that to choose a length scale that's small enough where you'd have a one-dimensional transient in the shock wave itself or in the shock layer itself, you'd be violating the continuum approximation anyhow. But for a combustion wave, you can, a flame can be about maybe that wide sometimes. And you could imagine there's all sorts of stuff that you could do that basically mess with the structure of the flame, and you need to consider that stuff. But for this analysis, we're assuming it is 1D, Cartesian 1D, and it is steady state. We will relax the Cartesian 1D and go to radial 1D when we discuss something called detonation shock dynamics. which is interested in looking at the effect of curvature on the propagation velocity, on the propagation of a detonation wave. Okay, but we'll get to that probably next week. Okay, and then any other questions? Okay, and then we'll do conservation of energy, and that is identical to conservation of energy that you've done a bajillion times. You just got the total enthalpy going in and the total enthalpy going out. And because there are no gradients, there is no diffusion heat flux or conduction heat flux on the sides, and there is also no viscous shear work on the sides. And so basically, you go through a whole big control volume analysis just to show that the total enthalpy entering and the total enthalpy leaving is the same. Okay, and just recall that the total enthalpy is defined as the internal energy, which includes the enthalpy of formation and the internal energy departure. It includes the kinetic energy, and it includes P over rho, which is the flow work. Okay, and so, but this is true for an inert gas or a reactive gas or a reactive solid. It does not matter what it is, that basically the total enthalpy is the same entering and leaving. And that algebra is fairly straightforward. And I'm going to call this in Scott Stewart notes, which I think some of you have looked at. Certainly, I think Braden had a stack of them on his desk for a while. Is that basically this is called cap H, okay? And that basically these so that in summary here we have conservation of mass, momentum, and then basically energy. And basically what these are basically saying is that the mass flux is invariant across the combustion wave. This here is you'll sometimes see this called the P U squared plus not P rho plus P is sometimes called stream thrust. And the only reason I remember that is because Ken Cole asked us that on an exam, and it's a bit of an antiquated term that we never heard of, so we all got that wrong, and he let us know. And he let us know that we all got that wrong. So I will never forget that this is called stream thrust. Okay. And then we're just defining this as cap P. This is cap M, and then we just have that the total enthalpy, or the total enthalpy entering and leaving the combustion wave are the same. Okay, and so these here are identical to the ones that you have for gas dynamics for a shock wave. No different. The only difference is the enthalpy of formation that is inherent to the definition of internal energy. That's it. And then so for combustion, we have two cases that we are interested in. One is that there is no change in chemical composition. That's an inert wave. That would be a shock wave. And we have that the products are at chemical equilibrium, and that would be the condition for a reactive wave. But for either case, these equations do not change. They are the same. Okay, and so their analysis is a lot like what you did for gas dynamics, for those of you who've took comp flow or gas dynamics. Okay, and so we're going to work with these a bit. We're going to work with the Rankine Hugoniot conditions. First, we're going to eliminate the velocity, and we're just going to use the fact that the mass flux is constant, which implies that basically we can solve basically the constant mass flux, which is equal to rho u, and we can just solve for u. And u is just the mass flux times the specific volume. And just recall that the specific volume is just 1 over rho. again, we will find out that as we work with these, that the Rankine Hugoniot analysis is more natural to work in terms of specific volume rather than densities. Okay. And so we're going to substitute this into momentum, and recall that momentum stated that that the stream thrust, or cat P, is constant, and that's equal to the pressure plus, that should be plus the pressure plus rho u squared. Okay, and then we basically solve this for pressure, and we have P equals, man, I missed that side, multiple places. Okay, which has that the pressure is equal to the stream thrust minus minus rho u squared, or it's equal to the stream thrust. I'm going to substitute in this minus the mass flux times the velocity, and I can substitute in this here. I had basically, this would be rho u squared equals rho u, which is m, and I have another m, so that's m. And so finally, I would wind up with that the pressure is equal to the stream thrust minus the mass, or minus the mass flux squared times the specific volume. And this is why it's more natural to work in terms of specific volume, is that here we have a relationship between pressure and specific volume in terms of two constants. We have P, or we have the stream thrust, and we have the mass flux squared. And we have a straight up linear relationship between pressure and specific volume. And this line here is it is called a Rayleigh line in the PV plane. Okay, and note this relation here applies to any state. It can be 1 or 2 or state 3 if we're considering a state 3. Okay, and these constants P and M squared are set by state 1. Okay, and so basically these are basically just the slope and y-intercept of our line. Okay. So, or I can rearrange this. I can basically use the fact that basically P1 is equal to cat P minus M squared times V1, and P2 is equal to cat P minus M squared times V2. And I can solve for basically P2, and I can take this relationship here and solve for M. And so this this cap M, again, is nothing more than the mass flux, or M dot double prime. And if you've done mechanical engineering heat transfer, you're used to that double prime notation. It's that. And we can solve for this, and it's just the square root of P2 minus P1 divided by V1 minus V2. Okay. And so first of all, what we can conclude is, A, not only does the pressure volume relationship does it give a perfectly straight line regardless of the equation of state. This does not require an ideal gas law. This works for any material, for any equation of state. It could be some crazy quantum plasma or anything like that, and it would still be a straight line. We have made zero assumptions on the equation of state here, none. And so basically this expression here also tells us quite a bit. It looks like a fairly benign square root term, but we note that this has to be greater than 0. So that means if we have a combustion wave that is increasing pressure, this implies that the specific volume of the reactants must be larger than the products. Otherwise, we have a complex valued mass flux, and that makes no sense. At least for my combustion waves. So that is, if the pressure increases across the combustion wave, we can conclude from this expression here that that the density increases along with the pressure, which sort of makes intuitive sense. And if the combustion wave decreases pressure and flames decrease pressure slightly, then basically we conclude that you can conclude that that the density at state 2 will be less than that of the reactant state. And again, that sort of makes intuitive sense. If you have a candle flame, there will be a flow above the candle, and a lot of that is generated by the fact that you are expanding the gas by about a factor of 10, and so the density of that high temperature gas is going down, and so that basically makes sense. So if we draw these Rayleigh lines on a plot, we get something that basically looks like this. We have state 1 here. This is often called the origin. And based on our square root relationship for the mass flux, we can basically block out these regions here as forbidden regions. Is that we basically wind up with a complex valued mass flux, okay, which basically makes no sense. And then basically emanating from the origin are these lines right here. And these lines are called Rayleigh lines. Okay, and the slope of these Rayleigh lines is basically minus of the mass flux squared, and the slope is just dp dv. Okay, so are there any questions with this? Okay, so I'll move on. So now we've determined, we have worked with mass and momentum to determine Rayleigh lines. Now we need to, and so basically, if we pick a Rayleigh line, that basically says that the solution to our combustion wave must lie somewhere on this Rayleigh line. And now to pin down where it can, to pin down more precisely where our solution lies, we need to consider energy and determine a relationship in the PV plane based on energy. And so we will work with energy and recall that the energy stated that there's no change in the total enthalpy across the combustion wave. And so the total enthalpy, we'll just call that cap H. Again, this is following the detonation nomenclature that is used a lot in the theoretical detonation world. Okay, and I'm going to take this total enthalpy and expand it into a sensible enthalpy and a kinetic energy. Okay, and so I'm just going to play with this a bit more. So we have that the sensible enthalpy plus the kinetic energy. Well, you can use our relationship between the velocity, the mass flux, and specific volume to show that the sensible enthalpy plus mv squared is equal to capital H. And you can show this probably be a bit of it's fairly simple algebra, but you can show I'll probably give it as a small homework problem. You can show that H2 minus H1 is equal to this expression here. Okay, or actually it's not sensible. This was just H. Sorry about that. So this here was just H. It was not sensible yet. Sorry about that, guys. Okay, and so we have the change of enthalpy across the combustion wave is equal to basically this term here. And I'll discuss physically what that is on Friday. And then, or you can cast this in terms of sensible enthalpy, the change of sensible enthalpy, but and that's equal to the same sort of work term here. This is this term does come from change of kinetic energy and work. And this, but since we work with sensible enthalpy, we do have to add a chemical energy term here. And in terms of doing analysis, to me, it's more intuitive to sort of add this Q here and work in terms of a sensible enthalpy. But if you're doing a computation, it's often more straightforward in the computer code that you would write to work in terms of basically in terms of an enthalpy that includes the enthalpy of formation. Okay, we'll call that HS does not include enthalpy of formation. Okay. So are there any questions with this? Okay, and note that the Hugoniot relation for an ideal gas, if I was to use an ideal gas with constant specific heat, you could show that P equals gamma minus 1 rho E. You can show that if you use the ideal gas law with constant specific heats, gamma equals Cp over Cv, you can show that this expression here is a hyperbola. Okay, and so the Hugoniot curve is for an ideal gas a perfect hyperbola, and even for a crazy high explosive charge that has a extremely non-ideal equation of state, the curve is still roughly is still very hyperbola shaped. It's just that it's not quite the same, just due to the non-ideal behavior introduced by the equation of state. Okay, and so I'll just show the last thing I'll go over today is just go over is that we can sketch the Hugonios. Here is that if we have a Hugoniot that if Q is equal to 0, then that means at state 1 there is no change in the enthalpy, and so basically if we have an inert wave, the Hugoniot will essentially be a hyperbola, and it will cross through our origin at P1V1, and so this here would be a Hugoniot if Q is equal to 0, if we have no heat release, and if we increase, if we now add chemical energy to this, essentially increasing Q, which means we now have exothermic chemical reactions. They are adding energy. They are adding sensible enthalpy, and then these are essentially shifting the Hugoniot curves up. And so if we have a positive heat release, we basically shift these Hugoniot curves up, and the higher the heat release, the basically more we shift the Hugoniot up. And if we have an endothermic chemical reaction, which is also possible, we shift the Hugoniot curves down. Okay, and so that should be intuitive, or not, I guess not intuitive yet, but in general, if Q is greater than 0, we have exothermic chemical reactions. These produce so-called deflagrations and detonations. We'll go over both. In terms in deflagrations, we will be going over a propellant combustion, which is a deflagration wave, and we'll be going over detonations, which are detonations. Endothermic, we deal with those if you're dealing with say hypersonics, and you have shocks that are so strong they are dissociating the air. That is a chemical reaction process, not unlike combustion. It's not self-sustaining, so it's a bit different. But you can also analyze a dissociating shock using this Rankine Hugoniot analysis. Okay, but we're not going to go over those in this class. And then Q equals to 0. That's inert, and that gives you the same shock Hugoniot that you may have learned about in gas dynamics. Okay, and so that is it for today.
Professor, I had a quick question about the Rankine Hugoniot curve you showed. When it goes endothermic and exothermic, why are they allowed to pass through the forbidden regions?
Oh, I was just drawing them in general. They do not pass through. A valid solution will never be in the forbidden region. But
Okay.
basically, I'm just drawing the entirety of the curve itself.
Okay. Okay.
Okay. You can show that basically, mathematically the curve will exist inside of the forbidden region, but it's physically nonsense there.
I see. I see. Thank you.
Yep.
So then what happens, is that like a jump condition then, where they would jump from the edge of that physical point to the other side? No?
No, we're gonna go over this basically first thing on Friday, is that basically this region here, in
We
this
can't
region
see your
here,
screen right now.
what's that?
We can't see your screen
Oh.
right.
Is basically this region here and this region here, they don't, is that the solution doesn't sort of ride along this and change on the Hugoniot as a function of time, is that basically it'll either be 0, 1, or 2 fixed points on the Hugoniot curves, and the solution will basically stay there. And the type of wave is determined by basically where the solution point lies, and the solution point is determined by where a Rayleigh line crosses crosses the Hugoniot curve, and so that is the solution to our system. And basically where these dots lie tells you what kind of combustion wave that this is. So basically these dots up here, this branch up here, it's called the upper branch. That produces detonations. And the branch down here, it's called the lower branch, and that gives rise to deflagration waves. And they have completely different properties. And basically we'll be going over this more on Friday. But basically detonations massively increase the pressure and change the specific volume a little bit, because they're on the very steep portion of the Hugoniot. And a deflagration wave massively increases the specific volume, but slightly decreases the pressure. And so it's not that the solution can jump from one to the other. Even in what's called deflagration to detonation transition, or shock to detonation transition, is that the flame does not jump to a detonation like this. That's not how it works. Okay, is that they are basically two distinct boxes, and they're two completely different types of waves, and we need to analyze them each in turn. Okay, does that make sense, or is that a bit too much for now?
No, that makes perfect sense. Thank you.
Okay, any other questions?